Welcome to Lecture 19, Friction, Wedges, Screws, Flat Belts. In this lecture, we'll look at wedges, frictional forces on screws, and frictional forces on flat belts. A wedge is a type of simple machine used to transform an applied force into a much larger force, and this much larger force is usually directed at approximately a right angle to the applied force. In other words, the angle of the wedge is very small or shallow. Wedges are also used to slightly move or adjust heavy loads. Let's look at an example where a wedge is being used to lift a block of weight W by applying a force P to the wedge, as shown in the figure on the left here. And so if the block is going to be lifted, we know that the impending motion, the direction of motion of the wedge is to the right. So that's important because we need to show which way the frictional forces will be acting in these problems. If we know the direction of motion, then we will know which way the frictional forces should be acting to oppose that motion. So let's look at a free body diagram of the wedge and of the block. And that middle figure there, we show the free body diagram of the wedge with the normal forces acting on the two surfaces of the wedge and the frictional forces opposing the motion of the wedge, and the free body diagram of the block showing equal and opposite frictional and normal force for where the block contacts the wedge, and then the normal force and frictional force at the wall, on the wall surface of the block, that frictional force acting to oppose the motion of the block rising up the wall. So I've asked, how many unknowns are there here? Well, one thing we need to say is that we are not concerned with tipping in this problem like we were in previous friction problems. So we're not, given that, we're not concerned with the exact location of the normal forces. Remember, those normal forces we're showing as a concentrated load. There's really some load distribution there along those surfaces, but since we're not concerned with tipping, we're just going to show the normal forces acting anywhere on those surfaces. But in doing this, we have eliminated the moment equation of equilibrium from our three equations that we have available to us for each free body diagram. Okay, so let's look at how many unknowns we have first. So we have P is certainly unknown. We're going to assume that we know theta and that we know the coefficients of static friction for the various surfaces in contact. So the normal force here is unknown, and we could say that the frictional force associated with that normal force is unknown. So at this point we would say we had three unknowns, but remember, we can express that frictional force as a function of the normal force, since as in the last lecture we saw that the frictional force is equal to the coefficient of static friction multiplied by the normal force. So this is really just one unknown here, assuming we know the coefficient of static friction. Okay, so we have two unknowns. This is another unknown. Okay, again, F sub 2 can be expressed in terms of N sub 2. So that's 3 unknowns. Here's F sub 2 and N sub 2 acting in the equal and opposite directions. So that's not an additional unknown. And here's F sub 3 and N sub 3. So we have 1, 2, 3, 4 unknowns. And again, we assume we have the angle theta. They've given us the angle theta. They've given us the coefficients of static friction. And of course, we also need to know the weight in this example. And the weight of the wedge we're going to ignore because the weight of the wedge is usually insignificant compared to the weight of the load that's trying to be affected. So we have 4 unknowns between these two free body diagrams. We would normally have 3 equations of equilibrium. This is 2D rigid body equilibrium. We would have 3 equations available for each free body diagram, but we already said we have eliminated the use of our moment equations based on our assumptions. So we have 2 equations of equilibrium for this free body diagram and 2 more for this free body diagram. Those equations being sum of forces in the x direction equals 0 and sum of the forces in the y direction equals 0. So we have 4 unknowns and 4 equations available. So we should be able to solve an example of this type. Now let's consider the same example, but instead of using the wedge to lift the block, we're going to use the wedge to lower the block. So in this case, the impending motion is going to be in the opposite direction. And our frictional forces are going to be reversed. Similar free body diagram, just with the frictional forces reversed. And depending on the angle theta and the coefficients of static friction, there may be a force P required to hold the wedge in place. In other words, without P being applied to the wedge would slip out due to the weight of the block. So in this case, you would find that P is acting to the right to hold the block in place. Another case is that the wedge is known to be what is called self-locking. In other words, that there's no force P required to hold the wedge in place. The frictional forces alone will hold it in place. And then the problem becomes finding the value of P that acts to the left required to unlock the wedge and allow motion to occur, thereby lowering the block. Screws are commonly used as fasteners, but they're also used to transmit power or motion from one part of a machine to another. Look at just about any 3D printer and you'll see long lead screws being used to either position the extruder or the build plate in one of the three axes. A common type of screw used to transmit power is the square threaded screw shown in the figure. Before we look at the equations for the impending motion of a screw, we need to establish the relationship between the lead angle and lead of a screw. The lead angle shown here is the slope of the thread, and we'll call that theta. And the lead is the vertical distance traveled caused by one revolution of the screw. So in other words, if you had a collar riding up and down this screw, then if you turned the screw one revolution, 360 degrees, the collar would move up or down by the amount of the lead. And we'll denote that by small l. Now, the lead angle theta can be expressed as a function of L, the lead, and R, which is the mean radius of the screw, which will usually be given in the problems involving screws. It might be given as the mean diameter, in which case you just divide it by 2. And theta is equal to the inverse tangent of the lead, the vertical distance caused by realized by one revolution of the screw, divided by the horizontal distance associated with one revolution of the screw, which is just the circumference of a circle whose radius is the mean radius. So if you know L, small l, and small r, the mean radius, you can calculate the lead angle of the screw. Now let's look at the equations associated with the impending motion of a screw. So we have this situation in the figure where we have a screw that moves up and down in a stationary threaded collar that's attached to the wall here. So the collar doesn't move, but the screw obviously is moving up and down as it's turned. And we have the top of the screw loaded with a weight W. And M is the moment applied to the screw by obviously somebody applying a force, a horizontal force to the handles here to create that moment. So for upward impending motion, in other words, what moment is going to be required to get the screw to turn counterclockwise, which will cause it to travel upward and lift the weight that is applied to its top. And we can calculate that moment with this equation, where the moment is equal to the mean radius of the screw times the weight that is acting on the top of the screw, times the tangent of the sum of the lead angle of the screw plus the angle of static friction of the screw. And remember from the previous lecture that the angle of static friction is equal to the inverse tangent of the coefficient of static friction. And that static friction is occurring between the threads of the screw and the threads in the stationary collar here. Those surfaces are where they're contacting within the collar. So to cause the weight to move upwards, the screw to turn counterclockwise, the weight to move upwards, you would use this equation. And note that if the angle of static friction is greater than the lead angle of the screw, then the screw will remain in place when the moment is removed. And that's also known as the screw being self-locking. So in other words, when there's no moment applied to it, and the weight is still there, that it's not going to spin the other way and move down. The weight isn't going to backdrive the screw. So along those lines, let's skip the middle equation and drop down here to the third equation, which is where you have the situation where the screw is self-locking, meaning that the angle of static friction is greater than the lead angle of the screw. So you're trying to find what moment is required to lower the screw in the collar, thereby causing the weight to lower. Okay, so now the moment's going to be in the opposite direction. In other words, we're now trying to figure out what clockwise moment is necessary to get this self-locking screw moving downward. And the equation's similar, except for this difference that we're taking the tangent of, which is going to be the angle of static friction minus the lead angle. And then the third case is when the screw is not self-locking. In other words, what moment is required to keep the screw from unwinding due to the weight applied to the top of it. And that's going to be, again, a similar equation, but now you're taking the tangent of the lead angle minus the angle of static friction. In other words, the lead angle is going to be greater than the angle of static friction. If the lead angle is greater than the angle of static friction, you're going to have an unwinding case when there's no moment applied to the screw. And when the angle of static friction is greater than theta, then the screw is going to be self-locking and will not unwind on its own. Here's the equation associated with flat belts when a flat belt is used in a belt drive. That is, the belt is moving over a fixed curved surface, or in a band brake where the belt is fixed and the curved surface is rotating against that fixed belt. So here's the equation where T sub 2 is going to be greater than T sub 1. And as shown in the figure here, T sub 2 is acting in the direction of the impending motion. So this curved surface here is fixed. It's not moving. and we're dragging this belt over the fixed curved surface, and there's friction between the belt and the curved surface, resulting in T sub 1 being less than T sub 2. So you can calculate T sub 2 if you know T sub 1, if you know the coefficient of friction between the two surfaces. And this could be a static problem or a kinetic problem. In other words, for impending motion, you would use the coefficient of static friction between the belt and the surface. And when motion's occurring, you would use the coefficient of kinetic friction. And then you also need to know the angle of contact, and that needs to be in radians.